Hello, this is the 10th installment to ray optics, and today we are going to discuss about two thin lenses in contact. If you have two thin lenses in contact with one another, then what will be the equivalent focal length of this combination? Now, these are two convex lenses. Suppose we can consider, however, different types of lenses. These are double convex lenses that I have considered over here. We can consider a convex and a concave lens, or rather a plano-convex, plano-concave, double concave lens. Many cases to consider, but as of now, we are considering two convex lenses that have the focal lengths, the f1 and f2. So they have the focal lengths f1 and f2, and for a point object which is placed over here, let that be at the point O. First, the light ray from the point O, we'll consider a single ray only. The other ray can act along the principal axis through the optical center of both the lenses, and that passes through undeviated, so that's of no use. So the single ray that we'll be considering over here, that falls on the lens 1, and this is the lens 2. So this is the focal length for the lens 1, f1, and for the lens 2 it is f2. Now, had there been no lens or after that, then it would have supposedly directed the refracting light ray along that direction, but that would have been the case had there been no second lens. So that would have been somewhere here, where I would have said that the image is formed at V dash, or rather I would take it as I dash. V is for the image distance, so I will be taking as I dash as the point where the image would have formed for the first lens. Now, because there is the second lens, it bends the light ray further, and it bends it somewhere over here, and let that point be I, that is the final image formation point. Now, I'll consider a somewhat uh, middle point as the central or optical center of both these lenses, and from that I would be considering the object distance as u, and then the image distance for the first lens would have been v prime uh, till the point I prime, and then the final image, the actual image that has been formed, that will be at the point I, which is at a distance of v from that center. So we have three lengths to consider, lengths, but two lenses. Now, for the first lens, because we have already studied the thin lens formula, we can just put in those values where we have 1 over v prime, which would have been its image distance had the image been formed at I dash. So for the first lens, we would have had it as 1 over v dash minus the reciprocal of the object distance 1 over u, and that would have been equal to its focal length, that is 1 over f1. But we also have the second lens to consider. So for the second lens, what we have is, we have the image, we know that is formed at the point I, which is 1 over v. What about the object distance? Now, object distance is one which determines the image distance for a fixed focal length. Now, the focal length for the second lens is obviously f2, and what would have determined the formation of image at the point I is the direction of the ray towards the point I1. You see, let me use another ink to explain this to you. Uh, because the light ray from the first lens was directed along that line, as I'm drawing it right now with the red lines. So because it was directed along that direction, that allowed the second lens to drop the image at this point. Had that been directed to some other point on this, maybe over along this direction, then the deviation or the bending of that light ray would have been somewhere else on the principal axis. So what is determining is the direction of the light ray from the after getting refracted from the first lens itself. So considering that, we can take that, so that is determining the image distance, and considering that, what we get is that being the determining factor, that can be considered as a virtual object. So we have the object distance in this case as the image distance of the first lens. So that's where the difference lies. So I'm continuing with the red ink over there. So that is 1 over f2. Now because of that, what we are getting is we are getting the image at that point. Now what we need to consider is that we'll be adding up these two equations. But what would that lead to? Well, let's see. If we add up these two equations, then as far the left hand side is concerned, we finally have cancellation over there, 1 over v dash minus 1 over v dash, that cancels out, and what we are left with is 1 over v minus 1 over u, and that is equal to, over to the right hand side, we have 1 over f1 plus 1 over f2. Now if we would have had a single lens which would have given the image at a distance v for the object being placed at a distance u, then that would have had a focal length, let us say f. Then this can be treated as an equivalent focal length for both those lenses, the combination of them. So as a result of that, what we can say is that a combination of these two lenses is yielding a focal length whose reciprocal is equal to the reciprocal of the focal lengths of the individual lenses in consideration. Now for convex lenses, obviously we have the focal lengths to be positive. Now in case of concave lenses, as we know, in case of concave lenses considered, either both of them or any one of them, the focal length would have been negative, considering the sign convention that we often use. That is, to the right hand side of the optical center we have the positive direction, while on the left hand side we have the negative direction. And because concave lenses have their focus or foci mostly on the left hand side, they are virtual foci, so that is why we will be considering the focal lengths to be negative in case of the concave lenses used. Now if they are at a certain separation, if we are considering the two lenses and they are separated by a certain distance, let's say this is the first lens and this is the second lens, and they are separated by a certain distance, let us say d, then with the distance taken into consideration, we have the equivalent focal length as 1 over f to be equal to 1 over f1 plus 1 over f2, that is there, but we also have a factor d where we have negative of d over f1 times of f2. That is the equation of the equivalent focal length of a system where the lenses are separated by a distance d. Now again, if we are to consider the power, now the power of a lens, that is equal to 1 over the focal length, which means its unit is meter inverse, or taken as a diopter, symbolized with capital D. Now 1 diopter is therefore 1 meter inverse. So taking all these equations that we have studied so far in this video, what we have is the power of this lens combination would therefore be P, that will be the equivalent power, and that is equal to the sum of the power of both these lenses. Also, in this case, what we have is the power to be equal to, I'm writing it over here, so P, that is the equivalent power of this combination, that will be equal to P1 plus P2 minus D times of P1 times of P2. So that is how we determine the power in this case. Now we'll be doing the numerical segment of the ray optics part very shortly, after I've completed my series on ray optics theoretical part, that is. Uh, and in the next video, we'll be discussing about the refraction through single spherical surface, and then we'll be over to the lens maker's formula. So that's it from this video. Thank you for watching.